Dear students, today we are going to discuss about the line broadening mechanisms. The radiations coming out of a collection of atoms making transition between two energy levels E2 and E1 is never perfectly monochromatic. This line broadening mechanism is described in terms of the line shape function g omega. We have discussed this in our previous class. So if the intensity of light is plotted against the frequency, we get a bell-shaped curve. The light emitted by atoms will have a frequency spread d nu or d omega, with the most intense part appearing at the central frequency nu or omega. The emitted light is in the form of wave trains with an exponential damping. The line shape function describes the shape of the curve with the property minus infinity to plus infinity g omega d omega equals 1. G omega d omega is the probability that a given transition between the energy levels E2 and E1 will result in the emission of a photon whose frequency lies between omega and omega plus d omega. Hence, a photon of energy h nu may not necessarily stimulate another photon of energy h nu, but it may stimulate a photon which has an energy between h nu and h into nu plus d nu. There are a number of mechanisms which leads to the line broadening. They can be broadly classified into two categories. First one is homogeneous broadening and the second one is inhomogeneous broadening. First is about homogeneous broadening. If the broadening mechanism affects each individual atom in the sample to the same extent, then the broadening is said to be homogeneous. Natural broadening or collision broadening comes under homogeneous broadening. In such a case, the probability of absorption or emission of radiation of a certain frequency is the same for all atoms in the collection, or all the atoms in the sample will have the same central frequency nu0 and it has the same line shape. Thus, there is nothing which distinguishes one group of atoms from another in the sample. Second is about inhomogeneous broadening. In the case of inhomogeneous broadening, different group of atoms are distinguished by different frequency responses. That is, different atoms in the sample have slightly different frequencies for the same transitions. Doppler broadening and broadening due to crystal defects belongs to this category. Let us first discuss about the natural broadening. Even in the absence of collision and thermal motion, there is the inherent line width because of the finite lifetime of the excited state due to spontaneous emission. This is known as natural broadening and the line shape is a Lorentzian. So let us consider an excited atom. An excited atom can emit its energy in the form of spontaneous emission. Then the rate of decrease of atom from the excited level to the lower energy level or to the ground level is given by dN2 by dt equals minus A21 N2. Let this be equation number 1. The energy released during each transition is h nu 0 equals h cross omega 0, which is equal to E2 minus E1. Here, thus the energy emitted per unit time per unit volume can be represented as Wt equals dN2 by dt, modulus of dN2 by dt into h cross omega 0. Modulus dN2 by d2 can be represented as A21 N2 then into h cross omega 0. So from equation 1 on rearranging we can write dn2 by n2 equals minus a21 dt. On integrating the above expression, we get log n2 0 to n2 of t equals minus a21 integral 0 to t dt. So applying the limit, we can write it as log n2 t minus log n2 0 equals minus a21 t. So we can write log n2 t by n2 0 equals minus a21 t, that is n2 of t by n2 of 0 equals e raised to minus a21 t. So on rearranging we can write it as n2 of t equals n2 0 e raised to minus a21 t. We have already written that w of t equals a21 n2 into h cross omega 0. So substituting the value of n2, we get wt equals a21 instead of n2, substitute n2 of 0 e raised to minus a21 t into h cross omega 0. So w of t equals n2 0 a21 h cross omega 0 e raised to minus a21 t. Let this be equation 2. And this equation represents the variation of intensity of the spontaneously emitted radiation. So this equation 2 represents the variation of intensity of the spontaneously emitted radiation. Now let us consider the electric field associated with spontaneous radiation. We know that the intensity is proportional to the square of electric field, that is I proportional to E square, or E proportional to I raised to 1 by 2. Thus we can write E of t directly proportional to n2 of 0 a21 h cross omega 0 e raised to minus a21 t there, whole raised to 1 by 2. Substituting from equation 2. Thus we can write E of t equals, again on rearranging we can write E of t equals E0 e raised to I omega 0 t e raised to minus a21 t by 2. But a21 equals 1 by tau sp. Therefore we can write E of t equals E0 e raised to I omega 0 t into e raised to minus t by 2 tau sp. Let this be equation number 3. From equation 3 we can write that the electric field associated with spontaneous emission decreases exponentially. Thus, to calculate the spectrum associated with the wave described by equation 3, let us take the Fourier transform. So writing the general form, that is E bar of omega equals minus infinity to plus infinity E of t e raised to minus I omega t dt. That is E bar omega equals integral minus infinity to plus infinity, and substituting the value of et from equation 3. Then we can write E bar of omega equals minus infinity to plus infinity E0 e raised to I omega 0 t e raised to minus t by 2 tau sp e raised to minus I omega t dt. Taking E0 outside the integral, then we can write E bar of omega equals E0 integral minus infinity to plus infinity e raised to I omega 0 minus omega into t minus t by 2 tau sp into dt. On integration, we get it as e bar omega equals E0 e raised to I omega 0 minus omega t minus t by 2 tau sb integral 0 to infinity by I omega 0 minus omega minus 1 by 2 tau sb. Here, as time cannot be negative, the integral is taken from 0 to infinity. So we can write e bar of omega equals E0 I omega 0 minus omega minus 1 by 2 tau sb into e raised to I omega 0 minus omega into t into e raised to minus t by 2 tau sb within the limit 0 to infinity. So on applying the limits and on further simplification, we get e bar of omega equals E0 by I omega 0 minus omega minus 1 by 2 tau sb e raised to infinity into 0 minus 1. So it can be written as e bar of omega equals minus E0 by I into omega 0 minus omega minus 1 by 2 tau sb. So on rearranging, e bar of omega equals E0 by minus I omega 0 minus omega plus 1 by 2 tau sb. That is e bar of omega equals E0 into 1 by 2 tau sb plus I into omega minus omega 0. Here t equals 0 is the time at which the atoms start emitting radiation. Then the intensity I proportional to or I omega proportional to e bar omega square, intensity proportional to square of the amplitude. Thus the frequency spectrum associated with the intensity distribution is given by I omega proportional to e bar omega modulus e bar omega square. So squaring the value of e bar omega gives E0 square plus omega minus omega 0 square plus 1 by 2 tau sb square. I omega proportional to E0 square by omega minus omega 0 square plus 1 by 4 tau sb square. Hence we can say that the line shape function associated with the spontaneously emitted radiation, that is g omega equals a constant k into 1 by omega minus omega 0 square plus 1 by 4 tau sb square. Here k is the constant of proportionality and which is determined by the normalization condition of g omega. Normalization condition is integral minus infinity to plus infinity g omega d omega equals 1. Then substitute the value of g omega. So we get integral minus infinity to plus infinity k into 1 by omega minus omega 0 square plus 1 by 4 tau sb square d omega equals 1. That is k, taking k outside the integral, that is k integral minus infinity to plus infinity d omega by omega minus omega 0 square plus 1 by 4 tau sb square equals 1. On further simplification, we get k equals 1 by 2 tau sb into pi. From this we can write k equals 1 by 2 pi tau sb. So we have already derived the expression for g omega equals k into 1 by omega minus omega 0 square plus 1 by 4 tau sb square. Again substitute the value of k. So we get the line shape, normalized line shape function g omega equals 1 by 2 pi tau sb into 1 by omega minus omega 0 square plus 1 by 4 tau sb square. That is g omega equals 1 by 2 pi tau sb into 1 by omega minus omega 0 square 4 tau sb square plus 1 by 4 tau sb square. that is by taking LCM. That is g omega equals 1 by 2 pi tau sp into 4 tau sp square by omega minus omega 0 square 4 tau sp square plus 1. That is g omega equals 2 tau sp by pi 1 by 1 plus 4 omega minus omega 0 square tau sp square. And this form is called as the Lorentzian. The full width at half maximum of the Lorentzian is given by delta omega 0 equals 1 by tau sp. So the above equation of g omega can be written as g omega equals 2 by pi delta omega 0 into 1 by 1 plus 4 omega minus omega 0 square by delta omega 0 square. And this kind of broadening is called as natural broadening. That's all. Thank you.